Black holes, unraveling the cosmic enigma. Black holes have long captivated physicists and astronomers, standing as some of the most enigmatic and awe-inspiring phenomena in the universe. These colossal entities, with their immense gravitational pull, challenge our understanding of gravity, space, and time. For over a century, black holes have piqued scientific curiosity, evolving from theoretical curiosities to confirm cosmic realities. A black hole, potentially 2 to 4 million times heavier than the Sun, wields tremendous power, yet remains largely invisible, detectable only through indirect means. Decades of research have transformed our understanding, revealing intricate details about these mysterious objects, often in unexpected ways. Recent advancements, such as those announced by researchers at the Kaku Institute, claim to have peered inside a black hole, unveiling aspects of the universe previously overlooked. This article delves deep into the nature of black holes, exploring their fundamentals, historical discoveries, recent breakthroughs, and the tantalizing possibilities they hold, such as connections to wormholes and time travel. The fundamentals of black holes. To grasp the significance of recent revelations, we must first understand the core principles of black holes. While the concept of a black hole is familiar to many, significant gaps in comprehension persist. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape its pull. This defining characteristic renders black holes invisible, making them both fascinating and daunting. Anything that ventures too close is inevitably drawn and compressed and lost forever in a region known as a singularity, a point of infinite density where the laws of physics, as we know them, cease to apply. The theoretical foundation for black holes emerged in 1916 when Albert Einstein introduced his general theory of relativity. This groundbreaking framework suggested that massive objects could warp space-time to such an extent that black holes could form. However, at the time, black holes remained speculative, lacking empirical evidence. It wasn't until the 1960s that scientists uncovered strong evidence for their existence while studying the binary star system Cygnus X-1. Astronomers observed an unusually bright blue star emitting X-rays, orbiting a massive, invisible object. Further investigation revealed that these X-rays were being drawn toward this dark entity, confirming the presence of a black hole. This discovery was a monumental milestone, proving that black holes were not merely theoretical constructs, but tangible phenomena in the cosmos. The significance of this finding cannot be overstated. It introduced a new category of celestial objects, demanding urgent and meticulous study. The first confirmed black hole, Cygnus X-1, located approximately 6,000 light-years from Earth in the Cygnus constellation, is far brighter than our Sun and possesses a gravitational pull so strong that it traps light itself. This defining trait, its ability to prevent light from escaping, earned it the name black hole. The discovery of Cygnus X-1 ignited global interest, prompting researchers to focus on these enigmatic entities with renewed vigor. The scale and prevalence of black holes. Following the discovery of Cygnus X-1, astronomers intensified their search for additional black holes. Current estimates suggest that the Milky Way galaxy alone may contain up to 100 million black holes, though identifying them remains a formidable challenge. Their immense gravitational force makes them cosmic vacuum cleaners, drawing in everything within their reach, including light, gas, and dust. At their core lies a singularity, where matter is compressed into an infinitely dense point. This process is both slow and extreme, stretching and compressing anything that falls in until it becomes part of the singularity, a phenomenon often described as spaghettification. Despite their prevalence, black holes pose no immediate threat to Earth. The nearest known black hole is approximately 500 light-years away, a distance vast enough to render any direct danger negligible. However, their sheer number and influence within our galaxy make them a critical subject of study. Black holes vary in size and type, ranging from stellar mass black holes, formed from the collapse of massive stars, to supermassive black holes, which reside at the centers of galaxies and can have masses billions of times that of the Sun. A historic achievement. Imaging a black hole. In 2019, scientists achieved a historic breakthrough by capturing the first clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. This monumental feat, accomplished by the Event Horizon Telescope EHD collaboration, involved a global network of telescopes working in unison to collect data over several nights. The resulting image, painstakingly compiled, revealed a glowing ring of gas and dust surrounding a dark central region, the black hole's shadow. This image provided unprecedented insights into the structure of black holes, confirming that they are not merely voids but complex entities with distinct layers. The black hole in M87, with a mass approximately 6.5 billion times that of the Sun, revealed three key regions. 1. The event horizon, the boundary beyond which nothing can escape. Once an object crosses this point, it is inexorably pulled toward the singularity. 2. The photon sphere, a region where light is trapped in orbit around the black hole, unable to escape its gravitational grip. 3. The singularity, the core of the black hole, where matter is compressed into an infinitely dense point, defying known physical laws. This breakdown of a black hole's structure highlights why studying them is both intriguing and challenging. The singularity, in particular, represents a frontier where conventional physics breaks down, pushing scientists to explore new theoretical frameworks. The complexity of black holes. Each black hole is unique, despite sharing a similar fundamental structure. Unlike other celestial objects that can be studied directly, black holes can only be observed indirectly through the radiation they emit or the behavior of surrounding matter. Sending a probe into a black hole is impossible, as anything crossing the event horizon is crushed into the singularity. Consequently, researchers rely on two-dimensional models to study these three-dimensional phenomena, adding a layer of complexity to their investigations. Black holes come in various forms, including stellar mass black holes ***, formed from the collapse of massive stars when they exhaust their nuclear fuel and can no longer counterbalance gravity. Supermassive black holes. Found at the centers of galaxies, these giants have masses ranging from millions to billions of solar masses. Primordial black holes. Hypothetical black holes formed in the early universe, potentially much smaller than their stellar or supermassive counterparts. The formation of black holes is most commonly attributed to the collapse of massive stars. When a star exhausts its fuel, it can no longer generate the energy needed to resist gravitational collapse. If the star is sufficiently massive, this collapse continues until it forms a singularity, surrounded by an event horizon. In the case of supermassive black holes, such as the one in M87, scientists observed a massive whirlpool of hydrogen gas rotating at 1.2 million miles per hour. Despite these extreme forces, the gas remained cohesive, indicating the presence of a colossal object, a black hole, holding it together. The Kerr solution and wormholes. In 1963, New Zealand mathematician Roy Kerr revolutionized black hole research by using Einstein's equations to model rotating black holes. Unlike static black holes, which collapse into a single point, Kerr proposed that rotating black holes form a ring-shaped singularity surrounded by an accretion disk of gas and thus rotating faster than the speed of light. This disk, known as the Ring of Fire, counterbalances gravitational collapse through its rapid rotation. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole, a hypothetical tunnel connecting two distant points in space-time, or even different universes. If black holes are linked to wormholes, they could theoretically provide shortcuts through space-time, enabling travel across vast distances or even to different points in time. However, wormholes face significant challenges. According to Einstein's theory of special relativity, the speed of light is the ultimate limit, making faster-than-light travel through wormholes improbable. Additionally, wormholes are likely unstable, surrounded by extreme radiation and gravitational forces, rendering them impractical for travel. Despite these obstacles, wormholes remain a captivating area of theoretical research. Some physicists speculate that stabilized wormholes could allow for time travel, though the energy requirements and physical conditions necessary for such phenomena are far beyond current technological capabilities. The idea of wormholes connecting to parallel universes further fuels scientific curiosity, suggesting that black holes may hold the key to unlocking the universe's deepest secrets. Unifying theories, superstring theory, and Hawking radiation. To fully understand black holes, physicists seek a unified theory that integrates Einstein's general relativity, which governs gravity on cosmic scales, with quantum mechanics, which describes the behavior of particles at microscopic scales. One promising candidate is superstring theory, which posits that the universe's fundamental building blocks are tiny, vibrating strings rather than point-like particles. These strings could explain phenomena such as black hole formation, wormholes, and other exotic solutions to Einstein's equations. Superstring theory also requires the existence of additional space-time dimensions, too small to detect with current technology, adding complexity to its validation. Another revolutionary concept is Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that black holes are not entirely black, but emit faint radiation due to quantum effects near their event horizons. Over time, this radiation could cause a black hole to lose mass and eventually evaporate. While Hawking radiation is too weak to detect with current instruments, it provides critical insights into black hole behavior and challenges the notion that they are eternal. The discovery of Hawking radiation also raises profound questions about the fate of information that falls into a black hole, sparking debates about the information paradox in quantum physics. Recent breakthroughs, peering inside a black hole, recent advancements, such as those reported by the Yaku Institute, claim to have provided a glimpse inside a black hole, revealing details previously thought inaccessible. While the specifics of these findings remain under scrutiny, they suggest that black holes may hold clues to aspects of the universe that science has yet to fully explore. These discoveries build on decades of progress, from the first detection of Cygnus X, to the imaging of the M87 black hole. By combining advanced observational techniques, such as those used by the EHD, with theoretical models like superstring theory, researchers are gradually unraveling the mysteries of these cosmic giants. The study of black holes also has broader implications. Their extreme environments provide natural laboratories for testing the limits of physics, from general relativity to quantum mechanics. Understanding black holes could shed light on the origins of the universe, the nature of gravity, and the possibility of other dimensions or parallel universes. Moreover, the sheer prevalence of black holes in the cosmos underscores their importance in shaping galactic structures and influencing cosmic evolution. The future of black hole research. As technology advances, so too does our ability to study black holes. Future observatories, such as the Next Generation Event Horizon Telescope or space-based telescopes, promise to provide even clearer images and more detailed data. Meanwhile, theoretical advancements in superstring theory, quantum gravity, and other fields may bridge the gap between relativity and quantum mechanics, offering a more complete understanding of black holes and their role in the universe. The challenges of studying black holes are immense, but so are the rewards. Each discovery brings us closer to answering fundamental questions about the nature of reality. Are black holes gateways to other universes? Could wormholes enable time travel? What happens to the information trapped within a black hole singularity? These questions, once the stuff of science fiction, are now at the forefront of scientific inquiry. Asterisk,